All right. Hello and welcome everyone to today's workshop on object detection. So this is a workshop run by the Meetup community at Beginners Machine Learning London. So we Meetup community on that we're interested in machine learning and implementation of most recent papers, as well as like latest advancements in the technology. I think what sets us apart compared to other Meetup groups is that we actually like to get our hands dirty and like start from the beginning and then go all the way to the end to more advanced concepts. So this is, we have a series of workshops that we are going to go forward with. Today's workshop is going to be mostly around object detection, and it's an intermediate level workshop. So we do assume that you have some background and familiarity with machine learning and deep learning. My name is Ali Parandeh, so I'll be your instructor for today. I'm a certified developer and data scientist and a software engineer. You can find me at LinkedIn below. And I'm also one of the founders of BML community, as well as I mostly work as a software engineer in the rail industry with implementing AI software and projects in particular and analytics solutions. So basically some of the stuff I will be sharing is some parts of my experience. The other parts are around a literature review of what's out there. And then those bits mostly we try to come up with my own resources for developing some of these workshops going forward. So we do have a curriculum in terms of like the workshops we have planned for 2022. You can see some of them here. So far, we've covered 3 of them. There were also a couple of workshops that did not fall into this curriculum. They're already uploaded on our YouTube channel. So if you would like to review those workshops as well, and these are the ones that have we already covered previously, you can visit our YouTube channel. I've posted the link in the chat. And then so you can catch up with the previous workshops as well. So today's workshop is going to be about CNNs, but in particular, the application of CNNs on object detectors, right? And then we're going to go into exactly demarcate between what object detectors are and what the different types of object detectors are and how are they different to semantic segmentation and style transfer and so on. So we're just going to brush up on a couple of previous concepts we've covered in our previous workshops, and then we will go into some of the concepts at this workshop that we'll cover today. This is just so that we can refresh your memory on some of the concepts around CNNs and TensorFlow. So if you have not already done so, you can go to this link to review some of the TensorFlow fundamental concepts. In terms of what we will be covering today is we're going to cover the differences between object detection and classification models. And we're going to look into most popular object detection models. In particular, there are two family of object detectors. There are region proposal object detectors, or two-stage models, and there is YOLO networks and one-stage models, such as single-shot detectors. So we're going to open them up today and figure out exactly how they work. I have my drawers with me as well, so I will try to also go into and draw around some of the concepts that are harder to understand. I will try to go and draw these out for you as well in terms of the conceptual parts of it. And then I will also show you how you can build an object detection model from scratch and how you can run object detection models on videos. So before I forget, I will also share these with you as well. So let me just open and share this with everyone. So I will post this link to the chat so you have access to it as well, and you can follow along. So if you go back to the slides, so object detection is actually a very hot area in computer vision, and in particular to not just computer vision, but like most other types of like applications in AI. In computer vision, it's very hard because you can actually use it to count things, monitor stuff, and optimize like processes, as well as like count usage or utilization rates of like various assets. So it has a lot of different applications. You can see like a couple of different object detectors in use in these videos that you see here. And basically, on these object detectors, you can see they're, I think, mostly using YOLO in the background. So YOLO is a you look only once object detection model. And on the left side, you can see that object detection can be used like in stations to count how many people are using some of the assets. You can also use object detection models in semantic segmentation models. Before we go forward, let me just open this up and provide the link for anyone to use the slides. There you go. So you can see that object detection can also be used in, well, they can be further enhanced to be used as semantic segmentation. And semantic segmentation is pretty much application of classification to every single pixel in an image and in a video. So once you take an object detection and you take it to the next level, it becomes semantic segmentation. So that is the subject of next workshop that we'll go to. And there's lots of cool things you can do with object detection. And you can actually train object detection models to detect anything within your own data sets. So that's a really cool part about it. And you can do transfer learning to do that. But before I go forward, let's recap some of the stuff we've learned with convolutional neural networks, because object detections and object detectors normally use convolutional neural networks as the backbone to perform feature extraction. So let's go through some of these concepts before we go forward into an actual, the details around object detection models. So the first thing we want to understand is that images in computers are stored as array of matrices and array of numbers. With grayscale images, you have one array of numbers, and the numbers in each cell represent the intensity of that cell. So 0 represents a black and 255 represent white. And if you have different color channels, so let's say red, green, and blue, these are represented by different matrices that then stack on top of each other. And the numbers in this matrix represents the intensity of that color channel. So you can basically use these color channels and use these numbers to represent any image you want in a computer. So that's how computers store images in the background. And any computer vision application you perform, any kind of like processing you perform on these images, they're going to be using this array of stack of matrices basically to perform them. Once you, when you take images and you pass them through a network, let's say a deep learning neural network, such as a convolutional neural network, you can see that the network starts learning on top of these images from left to right. And the way the network works is in the earliest layers of the network learns like, let's say, details around like shapes and around the shapes and like more simpler patterns, such as like lines and edges and like angles of lines and things like that. And as you progress through the network, as you see here, the network starts to learn more features and more complex patterns as you go from left to right through the network. So that's a very important concept to remember. It's because as we go through and understand how object detection models are going to be built, it's going to use basically the same principles of like how convolutional neural networks learn to extract features and identify features in images. So in this deep learning neural network, for example, like as you pass the images from left to right, you see that the layers that are basically further down the network, they learn to identify more advanced features of the images here, for example, which is pictures of humans. So more pictures of faces. So they then be able to classify what these images are and what these pictures are. And then one other thing we covered in the last workshop was that with deep neural networks, the whole reason we use convolutional neural networks compared to deep neural networks was because deep neural networks lose the context once you start to flatten them and pass the image through the flattened layers. So with images, if you notice with images, they have pixels that are positioned next to each other, and this data, this pattern and this data around the position of the pixels next to each other, these patterns and data is lost when you flatten the picture to pass them through a deep neural network. In contrast, when you use a convolutional neural network, the pattern and the data is basically when you use a convolutional neural network, that you slide a kernel across the image, and the kernel basically extracts the relationships between the pixels in terms of their positional relationships, as well as the context around what is inside the image. And you then create filters, a set of bunch of filters that then you can then use to construct your neural network as a feature extractor. So normally, typically, these feature extractors could be placed together. Like you can then use these convolutional layers and put them next to each other in order to construct a neural network that can be used as a feature extractor for your image. So if you just use a deep neural network, it's gonna cause you to lose the context around what your pixels are, where your pixels are, and like the shapes that are presenting your image. But if you use a convolutional neural network, you construct a series of layers using kernels, and these kernels then can represent your image in like lower dimensions, and in higher dimensions that allows you to then basically use these extracted features to like pretty much produce any kind of like output that you require. Right. So in this specifically typical or powerful CNN architecture, we take an image, which is a matrix of 227 by 227 array of numbers. They are in 3 color channels. And basically we slide a convolution under, and we construct 96 filters or 96 filters of 55 by 55. Then the next layer, we take a max pool, and we reduce the dimensions of the image to 27 by 27. We then do another convolution, and we create 256 filters of 27 by 27. We then do another max pool, and we reduce the size of the filters by 13 by 13, and we do that all the way down until we get a 6 by 6, 256 basically filters. So as we go down, we start becoming very deep in terms of like our layers. So we went from 3 color channels to 256 channels, which are our filters. And think of these filters as Instagram filters that like contain their features within our image. So the neural network can basically, you train the neural network to then use these filters as decision points around understanding what it is looking at. And then at the end, you put a classifier on top. This is our fully dense connected layers, which you can see is 9,216, then 4,096, 4,096, and then at 1,000 softmax layer. So in this neural networks, you are classifying an image into 1,000 classes. So this is a typical architecture of a CNN that you see that you can use in order to, train and to basically predict whether an image is a dog or a cat, up to 1,000 classes of different types of like images, categories, basically. The bit that would be very interesting for you to look at is like when we flatten the 256 layer. So once you perform the last max pooling layer and you get to the very long layer with 6 by 6 by 256, once you flatten that, you get 9,216 nodes, at which point then you can connect it to 4,000 nodes and another 4,000 nodes and then 1,000 nodes at the end. So normally your input and your output is fixed. So output, you know that you need, if you're doing a classification problem, you know that you need like, I don't know, 1,000 categories that you need to classify your images into. And in the input, you know the size of your image. But anything in between, you have the full control over. So the architecture of your CNN, as well as like how you're going to perform your, the operations, are your hyperparameters that you can play with. And normally there are some bunch of like popular CNN architectures that you can use and you can follow in order to construct your architecture. But normally it's like the main principle is that you need to start with basically a big image and then gradually reduce that down and make it really wide instead of make it really wide and make it really deep instead of making it wide and have a big height. So it starts getting really deep as it goes through the network. And the deeper you make the image go, the less parameters you need to use for your model to train, and the better the model will get trained. So that's why you see this pattern in the backbone of most CNN architectures. Another thing you will do as well to your images is that you normalize them before you pass them through the network. The whole reason behind that is that when you normalize your images, you go from the left to right, and the left is basically the loss. It's basically the loss function of your image in relation to the weight and biases matrices. So when you don't normalize them, depending on the linearness you use, your loss function can have a very hard time to converge towards zero. Whilst if you normalize your images, your loss functions, so the parameters become normalized. So like one in each and every update, you have a more stable progression towards the bottom of your loss function, or when you perform the gradient descent as you go down. So normally, when you build and train your neural networks with CNNs, you will want to basically go down and perform this normalization. The other part as well is with CNNs, you use filters. So depending on what kernels you use, this is an operation of what a kernel does. It basically is a sliding window that goes across the image and reduces that image down into a filtered image. And then the network uses that filter to basically make decisions on classification decisions or object detection decisions on that network. So think of a kernel as basically a sliding window that we send across an image, and then it basically reduces the pixels and the information in that image into another filtered image that is like either at the same size or at the reduced size. And with convolutional neural networks, you don't actually specify the parameters of those kernels that the parameters within those sliding windows. The neural network itself learns those parameters. So that's why the more layers you have, the better. The more layers and the more kernels you have, it's better compared to like having more wider pictures that you pass through the network. So these are like some of the examples of the different types of kernels that you can pass through the images. So each kernel has a different purpose. And normally you don't set these kernels when you train a CNN. The CNN learns to basically comes up with its own kernels when it creates those filters at each layer of the neural network. And this is how it works with color images. So with color images, you have a bunch of kernels that pass through each color channel, and each kernel is for each channel. And then basically at the end, the outputs are merged together. So that's how over time you can construct these basically neural networks, these CNN architectures. So you pass these kernels over the image, you construct this array of filtered images, and then you then do a max pool, which then what the max pool does, as the max pool layer slides across the image, it basically shrinks the image and keeps the signal in the image whilst removing the noise and compressing the image. Basically, it's one way of compressing the image down whilst keeping the signal and the patterns within the image. So that's why in these architectures, you see that after a couple of like series of convolutional layers, you normally will want to put a max pool layer to just basically reduce the size of the image down. Otherwise, you will have a lot of parameters in your neural network, and then like it makes it very much harder for the neural network to converge. So that's basically the recap of convolutional neural networks that we covered in the previous session. There is more details that is covered in the previous workshop that you can go and look at. But before I go forward into object detectors, I'm happy to take any questions. If you want to unmute yourself, I think you can able to do that. Otherwise, feel free to just post in the chat and I will answer the questions as I go forward. So Will asks, is there any explanation for the CNN architecture? What rationale behind why we treat the data for each process, or is it trial and error as a result? So these CNN architectures and the most 5 popular architectures that you see around the internet, like such as ResNet, LeNet, AlexNet, GoogleNet, and so on, mostly they've come up with, they have a general pattern around them, around how they are constructed. The whole reason they're constructed in this way, where you basically start creating more and more filters, but with reduced dimensions around each filtered image. This is mostly done by a trial and error, and they found that this is the best way in terms of like extracting features down and reducing the dimensionality of the data. But in terms of the general pattern itself, is that you start with a wide image and then you start shrinking down that width of that image, width and height, but start increasing the depth. So the number of channels, that is, as you go down within the network, because this way allows the network to have more filters as you go down and starts increasing the complexity of the way the network set can start to learn. And when you put the max pool layers in, it allows the network to get rid of the extra dimensionalities. So it kind of compresses the images down. So you have less parameters to work with. So it's always a trade-off between the number of parameters you have and the network learning some kind of like information about the pattern, the data you have. So you can then, you wanna construct your network architecture in a way that like, you still keep the context in the beginning. So if you see in this network, as you go down from left to right, you don't suddenly get rid of all the information. You don't start max pooling and you don't start getting rid of the dimensions and the width and height of the image. You gradually start reducing the width and height of the image, not suddenly, because in the beginning, you still want to capture as much contextual information around the positions of the pixels as possible. And then as you go down and you start encoding the image down into a very deep layer, it starts extracting that information as much as possible. The next question is 10,000 classification an upper limit? Not necessarily, no. So the last layer is a softmax layer. So you normally use softmax when you're doing classification on lots of categories. And it gives you probability class for each class, probability scores. So you can have as many classes as you want, as long as you have labeled them in the training process. So normally what you want to pass in is a labeled process. So basically labeled in classification tasks, you want to pass down basically images with labels, and you can have as many categories as you want. In particular, you just want to make sure that you have a balanced data set. So if you have a data set of 1,000 images, you don't want to have 999 images of a cat and then 1 image of a dog, because then your network learns a lot about the cat, but nothing about the dogs. So normally in these situations, you will want to oversample the dog, basically data, so that there you have at least a similar amount of data for the dog and similar amount of data for a cat. And one way you could do that is to augment the data set for the dog classes, and then combine that with a same amount of data with the cat classes. However, if you can get real data, it's better compared to if you use augmentation, just because you actually get real features compared to augmented features. Team asks, any success with CapsNet and object detection instead of using pooling? So I'm not familiar with the CapsNet. So I can basically look into that and get back to you, Tim. Tabridge asks, can we use DLCOM format image for object detection? So with different different formats, it depends what you have trained your model in. Normally with different formats of images, you can, as long as you can load them into memory and you can pass them down as an array of numbers to the network, you can use that format. Otherwise, you may want to decode that format into another format before you can pass them in. But any format, you can basically just, as long as you can decode them and load them into memory as an array of numbers, you can then pass them into the network. Because at the end of the day, the network requires the images to be an array of numbers. It's just that's the input of the network. What you could do is you could have a lambda layer, or you could have basically a data processing layer in the beginning of your neural network, where the network can then take the custom image format in as the input, and then within the network you process that image and you pass it down. That way you never need an extra pre-processing layer to be in place before you pass that image to the network. But whenever you define your network architecture and define your custom pre-processing layers, you will want to make sure that then you always treat that network in the same way, that you pass the raw data in its same raw format to the network. Don't pre-process it again anywhere. Any other questions? Just wait a couple of minutes, see if anyone has any questions. So just for the next part, what I'm going to do is I'm going to try to connect my drawing tool so that then I can draw some of the concepts in relation to object detection, whilst we wait for anyone who has more questions. How about now? Can you see the slides now? Perfect. So with this, now you can see that basically, in terms of the slides, you haven't missed much. So I was just talking about the slides here, and I will just go through it again due to some of the technical difficulties. So in terms of the going from classification to image segmentation, as you go from left to right in this slide, the problem becomes more complex and complex. So first you start with a classification problem, and you just have to classify a single class of an image. Then you have a localization problem where you haven't just classified the image, you want to actually draw a detection bounding box around where the object is. The next step is when you have multiple objects in the image and you want to classify different basically classes of objects within the image and drawing the bounded box around them. And at the last step, this is the most complicated part, which is you want to not just classify the objects in the image or detect them, but you also want to draw the exact boundaries of the object in the image. And this is called image segmentation. And the main step going from the object detection to image segmentation is to classify, not just find the bounding boxes of the object, but to actually classify every single pixel in the image into one of the class categories that you have available. So that's the main difference as you go from left to right in your object segmentation problem. Any questions so far on this? All right. So the only problem with that, with doing all of this, is that object detection is very, very hard. So like imagine like you have an image on the right-hand side and you have about 500 to 1,000 classes of like different categories that you want to detect. There's just so many things going on, and it just makes it really, really hard to classify pretty much everything, and you train some kind of object detector that can like see all sorts of different objects. Other than that, you have a problem called occlusion, lighting conditions, and just basically angle of view. So occlusion is just basically when an object is basically in front of another object, occluding parts of it. So a human can see that like I'm holding a phone behind my hand, but with a computer, if the phone is not fully visible, it makes it really hard for the computer to classify the phone. So training an object detector to be able to also detect an object, even if it's occluded, is very hard. Another problem is lighting conditions. So one of our friends just asked that, like, is it possible to detect the same objects at night? It's still, it may not be possible, like depending on what you're trying to detect. So lighting conditions could make it different. Again, with human vision, we can still, you know, identify if you're looking at a object 1 or object 2, but with computer vision and object detectors, it's still a very hard problem to solve. Like you may need to actually like train the model on like those instances where the object is in night vision. So based on that, it can be quite a hard problem. So Rayhan asks, would a classifier say 50% dog and 50% cat for a photo of a cat and a dog or not? So let's go back to answer this question. So if we have multiple objects in an image and the object detector is trying to detect an object, normally the output of the neural network will be not just where the object is. So you get the coordinates of the bounding boxes in terms of like, you can either get two types of the coordinate bounding boxes. You can get the coordinates of the bounding box, or you can get the center point of the bounding box with the width and height of the bounding box as the output. You can also get the class as the output, like which class this bounding box refers to, or which category it's predicting. And you can also get a probability score, which is a number between 0 and 1 or 0 and 100%, which shows how confident the network is in detecting this object. So Rayhan, to answer your question, yes, if you have cats and dogs in an image and the model is not very sure it's looking at a cat or a dog, you might get basically both detections that says, I can see a cat and a dog, and these are its bounding boxes. And I think like I'm like 50% sure or 60% sure this is a cat or this is a dog. And then it's up to you to then try to clean up those detections. So object detection by itself may not be enough. You may need to actually put a bunch of other Python scripts in place to clean and process those detections. And we go actually into some of those scripts in a minute. So when we go into object detectors as an area, there are actually basically two family of object detectors. They are called 1 and 2 stage object detectors. So the first stage object detectors are basically YOLO and SSD. So YOLO stands for you look only once, and single shot detectors. And the 2 stage detectors, or 2 stage / proposal detectors, are called RCNNs, or basically regional proposal convolutional neural networks. And you have a whole family of them, such as RCNN, fast RCNN, faster RCNN. I mean, it's very creative naming of these networks, but yeah, basically one is better than the other, right? And then at the end, you get the mask RCNN. And the mask RCNN, and then the 2 stage detectors themselves can, you know, break up into this kind of like architectures, as you can see. So you can compare and contrast how the architectures are different, but we will actually go and deep dive into how each one of them work and how they have actually improved over time. So if you just look at the mask RCNN and like you ask yourself, how the hell did these researchers come up with this architecture? That's not how it actually worked. Like they started, one person actually came up with the architecture of an RCNN, or regional proposals. And if you look at the idea behind RCNN, it's actually quite simple how they've done it. They just extended how a classifier works. And then they tried to use an RCNN to detect and localize objects in an image. And then over time, the same person and other people started improving on those architectures and methodologies until they reached mask RCNNs. And then later on, someone like PJ Reddle came and said, you know what, actually, I think we can do way better than that. And we can do the whole thing without actually having two stages in the process. We can just do the whole thing in one stages. And that's where YOLO models were born. And some of the commercial applications that you see of object detectors are normally using YOLO, SSD, or mask RCNNs. Don't start, RCNNs are actually very, very slow. So you normally won't see RCNNs in action or in practice. I will go into detail about them today just because it's important for you to understand how they work, because later on you can then understand how other object detectors work, even like the more advanced ones that haven't come out yet. But before I go forward, does anyone have any questions on object detectors and the family of object detectors? All right, no questions. Perfect. So let's start with the first one. So RCNNs. So I will actually go into taking you through what the one stage and two stage detectors mean. So one stage and two stage detectors are basically the two stage detectors. They are called two stage because in the first stage, the detector has to propose a bunch of regions. And then in the second stage, those regions are then classified. With a one stage detector, both the regions and the classification of the regions are done at the same time, at the same forward pass. So the two stage ones are basically, one stage is the proposal of the regions, and then the second stage is the classification of those regions. And then the one stage detectors are the whole thing, the whole proposal and the classification is done in the same stage. That's why they are called different stages of detectors. So if you go to the most basic one of detectors, we have of their two-stage detectors, we have the RCNNs. So these are called regional proposals, the convolutional neural networks. And this is an extract of the paper itself, where there is a four-stage process in place. In the first step is you have the inputs to image. You put that whole input image into the model, right? So you can see the model on the right-hand side there in the 3D space. What the model does is that it uses an independent algorithm. There are a bunch of them. Normally they use an algorithm called Selective Search to basically come up with a bunch of proposals around like the regions of the image that you should extract and then classify, right? So what the model does here is that it basically starts drawing like 2,000 different types of bounding boxes on the input image. And then it crops those bounding boxes out, right? So it has then 2,000 cropped bounding boxes. It warps them into a square image or basically into width and height that is suitable for the CNN that is in the next step. And then in the next stage of the pipeline, that warped image that is now basically, we called it warped because if you extract a rectangular bounding box and then you basically warp it into a square, you lose the aspect ratio and it becomes like a warped image. And then you pass that warped image through the CNN. And then at the end, you use an SVM classifier to classify like with what this object belongs to. Like, is it a cat? Is it a dog? Whatever, right? And then as part of that, you also get the coordinates of the bounding box, right? And then you have to use a bounding box regressor to then basically interpolate back or project back the bounding boxes you got into the actual image. Because remember, we're passing the warped region proposals down to the network. So we need to go back and we need to do some kind of regression in order to like be able to get back the original bounding boxes on the actual input image. So how many models do you think we're using in this basically RCNN right now? So this RCNN is going to be very, very slow. Do you know why? And do you know how many models we're using in this RCNN? So it's a 4-stage process, but it's using n number of models. Does anyone know how many models we're using? No idea. Apos is like, no, nothing, no idea. Guess a number, 1, 2, 3, 4, 5. 25. 2K. No, models, not number of images, number of proposals. So I'll tell you, it's actually not 1, it's not even 2. There's actually 3 models that are connected together to make this whole thing work, right? So this RCNN proposal, region proposals architecture right now that you see has a lot of limitations. So it's very, very, very slow, like in terms of hours, slow to train. And the whole reason is because you're not just training 1 model, you have to train 3 models for it to work. So the first model is the selective search model. So remember, like in the whole bit where we are extracting the region proposals, the 2K region proposals. So region proposal is basically the bounding box, the crop that we're going to take out, warp, and then pass to the network. So in that part, we use an algorithm called selective search. So selective search, basically what it does is it tries to come up with bounding boxes, but it's trying to do that in a more smart way rather than just some random bounding boxes. So what it tries to do is that it uses like edge detection and like other pieces of like information in the image, and then at different resolutions, it tries to then basically group different parts of similar parts of the picture together at like higher resolution, lower resolution, and like even much lower resolution, and then come up with like smaller, finer bounding boxes, much bigger bounding boxes, and like very, very large bounding boxes that could represent a whole object as a whole, as you can see here. So there are some examples here, like if you look at the example number B, like at a very high resolution, like it's trying to group lots of different types of like parts of the image together, and it's not doing a good job because you end up with so many different types of bounding boxes that like it's all over the place. In the second part, it tries to group much more similar parts of the picture together. So you can see this like color map of that grouping, and then it uses this color map to then come up with more bounding boxes. Now these bounding boxes may make more sense in terms of like whether they could contain an object within them. And then lastly, it then tries to come up one level higher. It's called a selective search. And then basically it then tries to group much more basically related pixels together, and then use those colored related pixels in order to come up with bigger, like higher level bounding boxes. And then at the end, it combines all of this together. It produces about 2K bounding boxes called region proposals, and then it then passes them up to the CNN. So this whole model can then be trained itself to produce better and better bounding boxes, and it can be also, you know, quite a time-consuming process, computationally expensive process to generate the bounding boxes. So that's the first part. That's the first bottleneck in this RCNN network. The second bottleneck is in the CNN itself. So you have the CNN, which could look like this. So that's your feature extractor. You have to train the CNN as well, other than just this selective search model. You have to basically train this CNN model as well. And then at the end, you have to train a bounding box regression model to basically unwarp back your coordinates, your bounding box coordinates back into the input image dimensions. So you will need to basically then use the some kind of regression model to basically take the coordinates of your bounding box and then regress them back into the input image, basically dimensions. Just because you are sending warped images up into the CNN, and then you need some kind of regressor to then translate back those coordinates from the warped image back into the image original width and height size. So that's why you can see it can be actually quite very slow, because you have to train all of these different models and they need to work together. And in each forward pass, like each image will need to have 2000 region proposals produced on it. Then these region proposals need to go through a classifier, then through the CNN network to get basically classified and feature extracted. And then you have an SVM and a bounding box regression model to then basically not just predict a class, but also translate the coordinates of the bounding box that is being detected as part of the image. So these were the main limitations of the RCNNs when they were proposed by the authors. And the same author that proposed this basically architecture and this method realized how slow this basic methodology was. And then he basically thought to himself that like one of the biggest parts of the model was having to pass every image through this whole process. So for each image, you basically have to take 2K region proposals, pass them through this CNN, and then in order to be able to do then classification and regression. So what he did instead was he thought to himself, what if instead of like duplicating instead of duplicating this whole process of like passing the whole image down, I could actually reuse the convolutional layers that I have gotten, and I could just basically take those convolutional layers and reuse them on the other images as well. So this way he saved basically time on this step of the process where he has to like pass an image through the CNN architecture. So if you go back and you look at the architectures here, there's difference between the RCNN and fast RCNN is that basically in the RCNN, you pass the image through the deep CNN network, right, which is pre-trained, and then you have to then combine them together and basically fine-tune the regional CNN features, and then pass that down to an SVM object classifier and a box offset regressor, right? So the SVM classifier detects the class of the object, the regressor detects the coordinates of the bounding box. With the fast RCN, basically what it does is that like you still have to do the selective search. You still have to basically take the 2K region proposals. But instead of like then passing the region proposals to this deep convolutional neural network, you then just use the features from the deep convolutional neural network that has been pre-trained. And you perform something called a region of interest pooling to create some kind of like a region of interest features. So the region proposals, what it does, basically in terms of what it does is that it has the CNN that is pre-trained, and it basically just takes the feature map of that pre-trained CNN on the images, and it then performs and passes the detector, the proposal over the network, and then it extracts the features out. And then it can then basically uses the region of interest pooling layer to extract the features out and compress the image down, so that then it can use it to perform softmax detection as well as regression for the bounding box. Right? So this is basically the image that's taken from the actual paper itself. So here you can see when it takes one image down, it basically takes the region proposals at the same time and performs the region of interest projection on top. And then once it passes through the last region of interest pooling layer, which only applies the pooling layer on the region of interest, that's why it's called the region of interest pooling layer, through a bunch of fully connected networks layers, it then basically connects them to two output networks. One is a softmax output network for basically performing a detection on the class, and then a regressor network for performing a bounding box detection. So that's the main difference between the normal RCNN and the fast RCNN. So this is another image from it. So instead of passing basically the selective search across, what it does is that like you have the convolutional neural networks, and then it passes the the image through the convolutional neural network, and it then extracts the region of interest from the proposal from the network itself, and then passes those feature map through the region of interest pooling, which then only performs the pooling across the region of interest to extract and encode the image down to basically a bunch of filtered layers. And then it then passes those filtered layers through the fully connected network. And then at the end, it has two outputs, one for the class identification and then the other one for linear bounding box regression. And the whole reason that this fast RCNN is more faster compared to the previous one is in the whole area, in the whole idea behind reusing your basically trained features within the network. So instead of like passing the whole image through the CNN all the time, it just passes these regional proposals of the network through the regional proposals of the image through the network, and performs the convolution and pulling over that only. So Abbas asks, if YOLO applied in that case, what would be the amount of time spent to get to the outputs? So YOLO is different in the way it works compared to regional proposals. So RCNNs are way slower, even like the fastest RCNN or mask RCNN is going to be way slower compared to YOLO networks, because it's a two-stage process compared to YOLO, which is a one-stage process. So YOLO only looks at the whole image once. That's why it's called a YOLO. And it performs the object detection and the classification at the same time for each object. So the next step after the fast RCN, which is basically to pass the image through the convolutional neural network backbone and then extracting the features out using a feature map, right? So we still use a selective search, and we perform the selective search on the feature map instead of like on the image. And then we basically create these bounding boxes, and then we pass those bounding boxes through the fully connected layers to perform the classification and regression. In the faster RCNN, we realized that the whole selective search process, which is this one, so this whole selective search process is also another bottleneck. So instead of having that as a separate model and then passing that through, why don't we combine all the steps of the process into one big, large CNN, right? Into one big, large model. And we call that a faster RCNN. So what that entails is that we have a CNN network that is called the convolutional backbone. So this is our feature extractor. And then we have instead of using a selective search algorithm this time, we have a part of the network called an RPN, or regional proposal network. And this regional proposal network is responsible for producing these bounding boxes or their region proposals. And then these region proposals are then passed through a region of proposal pool layer, which then compresses the amount of information that's passed through the network down. And then we have a fixed size feature map, that is the warped feature map. And then we pass it through the fully connected layer, which then allows us to then perform classification and bounding box regression. So the bounding box regression for detecting the bounding box coordinates. And then the classification for detecting the classes. So that's why we have to go through this whole process to get to that stage. And this is why we have a faster RCNN, which is like the next step down the process. And it's actually one of those methods as architectures that can be used at like some kind of like prod level process. So in the fast RCNN, what you end up doing is that you, instead of like passing the image through a selective search process and then take the proposals and then pass the proposals down to a CNN, you basically put the CNN first. So you rearrange the order of the architecture of the network and you combine all the parts of the network together. You then pass the image through the feature extractor, and then you take the feature maps, you pass it through a region proposal network to create a bunch of proposal parts, and then you pass that through a regional proposal pooling in order to basically create a very dense and rich and compressed feature map, which then you can then pass to the classifier to classify. And in terms of like what you could get at the end is you could even add anchor boxes in. So in order to make it more complex, the region proposal network itself, as it passes a sliding window across the feature map, it produces 256 dimensional immediate layer, which you can then use to classify into 2K scores or 4K coordinates. And the whole reason you might get 4K coordinates is because when you use anchor boxes allows you to then classify multiple objects in the same image that are like overlapping on top of each other. So you remember when I talked about occlusion. So when you say, when for example, you have an image of a person standing in front of a car is like a very wide object, but a person is a wide object in a height format. You use anchor boxes to basically tell the neural network that in each region proposal, I may have multiple objects. So try to detect objects in different orientations based on my anchor boxes as reference boxes. So this way you end up producing multiple like bounding boxes per region of the image or per region of the feature map. So that way you may end up producing way more predictions in terms of classes and coordinates, but at least this way you end up classifying all of your objects, even though they're standing on top of each other or like in different orientations and shapes. Any questions? So Abbas asks, YOLO and CNN can be used interchangeably or they have their own special use cases? So a YOLO actually uses a CNN as its backbone. So CNN basically is CNN is just the name of the convolutional neural network. So it's a name of the network type that is being used inside the YOLO. It's also the same type of network that is being used inside an RCNN. So they all use CNNs as their backbones or as their backbones of the networks. And basically what the CNN does is that it extracts features from the images down to the last part of encoding layer, which then you can attach classifiers and like other types of networks on top to basically produce new types of information from those feature maps that is being extracted. If you focus on the fast RCNNs and the last layers in the region of interest pooling layers, I just wanted to show you as well what the region of interest pooling could look like. So let's say you have a feature map that looks like this on the left-hand side, the input activation. When you do a region of interest pooling, you basically just take a piece of that feature map that you're interested in. So that's called the region of interest. And then you only perform the pooling layer, the max pooling layer within that region of interest. So you divide that region of interest into 4 sections, and then you just basically pick the biggest pixel that has the biggest value in that region of interest, basically. So this is called the region of interest pooling layer. So when you take region of interest, you just divide it by 4, and then you just take where the maximum pixel, you do a max pool of each of those regions. So that's the faster RCNN. Any questions before we go to the next type of RCNN, which is the last type? It's called the mask RCNN. Does anyone want to take a break before we go forward, like a 5-minute break? Otherwise, we can carry forward. All right. So what I'm going to do is I'm going to pause the recording. We can take a 5-minute break, 5-10 minute break. See if you can grab like any coffee or tea that you want, and then we can come back and then resume rest of the session. Perfect. So before we took a break, we basically discussed how fast the RCNNs work, and then the next stage after fast RCNNs are mask RCNNs. Now with mask RCNNs, there is one piece of information that's quite different about them that makes them different from the faster RCNNs, and that is called the way that they perform the pooling. So what mask RCNNs allows these RCNNs to do is it allows them to perform pooling at a finer level. So it uses something like a bilinear interpolation to perform exactly what's it called, like a more refined pooling and compression of the image, and preserving the information within that layer, right? So it's called an ROI aligned pooling. And this way, what it allows this typical architecture to do is that it allows the architecture to then perform a bunch of convolution layers at each pixel, right? So it then gives each pixel a class, right? So it allows the architecture to perform classification of each pixel. And this way, you can then perform segmentation of the image. So in order to perform image segmentation, you need to make sure that your max pooling layers are not getting rid of the information such that it makes it really hard to perform that classification. So when you change the pooling to an ROI pooling, ROI aligned pooling, it allows you to then preserve that information of the classes of that object, so that then when you perform the classification of each pixel, it allows you to then exactly detect where the objects are and basically classify them in terms of like their actual boundaries of that object instead of just a bounding box. So the main changes as applied in the architecture of RCNNs is in the head of the RCNN, which you still have the RPN and the CNN. So you still have the convolutional neural network. The image goes through the convolutional backbone, gets feature extracted, and then the feature map then goes through the RPN, or the region proposal network. A bunch of regions are proposed or extracted from the feature map, and then these feature maps are then passed through the ROI align layer. So then you get a very fine-grained pooling feature map that is extracted from that. So then a fixed size feature map then is connected to a head through a fully connected layers that goes through box regression and classification, and then another one goes through the mask branch, which then applies the mask that you can see on the left-hand side. So this way you can then mask your image by basically, the kind of output that you would get is basically the one that we showed here. So we might get a video. So if you pass the video through this whole mask RCNN, you might get something like this, where like every object in the image is kind of like masked. It's because you're actually classifying each pixel in the image. So that's the mask RCNN, and you can also like replace the pooling layer with other types of pooling, some of which are shown here. Now there's some like heavy maths going on for each pooling, but if you're interested, I've put the link below if you want to learn more about like how other different types of poolings there are. With most of these poolings, it's like either you just take a region of interest and you perform max pooling under, or you do some kind of interpolation in order to like identify like how much you need to like change around the intensity values of the pixels and reduce the dimensionality in the data and compress it. But when you are able to mask an image, that means you can actually take an image and you can perform semantic segmentation on top. That basically means you can perform classification of each pixel inside this image and basically take that image and figure out in each layer of the image where the object resides and what that object is. And so this way, a lot of like driverless car applications, for example, use semantic segmentation in order to understand the context around the cars, and basically that information is then fed back into the driving behavior of the car itself. But we will go more into detail in the next future workshops around semantic segmentation. We may actually get our hands dirty as well with some code. But what I wanted to take away with this, like this whole review of RCNNs, is the two-stage detectors are actually, even though they are they can be quite detailed, like especially with mask RCNNs. If you have any application that requires, you're not very much concerned with how like it takes to process the videos and the files and the images, but you more care about the accuracy, consider RCNNs, in particular faster RCNN and mask RCNNs, as the kind of object detectors to use for your application. And even though you might perform a mask RCNN and you might mask the whole image, you can still extract bounding boxes from that masked picture. Otherwise, you can use a faster RCNN. But these are different comparisons of the RCNNs, and you can see how the RCNNs have like progressed from left to right over time. And the time span between the RCNN and mask RCNN is only 3 years. So even though like the progress have been quite significant from left to right, the amount of time it took to go from left to right is actually quite short. So yeah, who knows what we'll see in the future. But this is all two-stage processes, right? So there are ways to actually improve efficiencies and performance and actually get detections much faster. And that is where single-stage object detectors come in. And you might have heard of some of them before. All the videos you saw in this presentation use a single object detector. In particular, for example, this one, where you see the cars like riding by. So these single object detectors are very useful if you want to apply them to real-time applications. So imagine like a camera looking at people and you want to count people in on and off into a retail market, supermarket. In real time, you can use a single stage object detector. So these object detectors actually are really, really performant, in particular with YOLO models. So if I look at this one, like a YOLO, you look only once object detector, can actually detect objects in real time. So the blue area of this whole performance chart shows that like these object detectors, as you increase the FPS value, the accuracy, actually the average precision, still remains relatively high, between 65%, for example, compared to all the other object detectors that are out there. So let's look at why single object detectors could be better compared to RCNNs. So if you notice, RCNNs use a CNN. So they use a CNN in particular. These CNNs, what they do is they pass a CNN through the whole network, sorry, through the whole image, and then the image, a feature map is then extracted from those images, right? But the main problem with sliding windows and when we slide kernels in these CNN networks across an image is that, first of all, we don't know the size that we need, the size of the kernel we need to slide across the image, and we don't know the shape that that kernel needs to be in order to extract that object out. That's why we need to like create all of these region proposals and figure out exactly like where the objects could be in order to like produce the bounding boxes around them. So that's the main limitation of RCNNs, is that like because they slide a kernel across the image, it's not exactly possible in the first step to figure out what the size of this kernel should be in terms of its shape and size in order to produce the bounded boxes. But another approach could be another approach that, for example, single shot detectors and YOLO take, is that instead of like passing a sliding window across the image and then trying to then come up with regions that we can then classify, why don't we take our image, divide it into a grid of boxes, and then try to classify objects into in each box and classify each box basically, and then figure out the bounding box based on that. So what we do here is we divide the image into a grid of like 4x4, and then we classify, we then try to figure out the class of each box. So the first box on the top right corner, top left corner is a pool. Then there's nothing, nothing, nothing. Then this one could also be a pool. The next one could also be a pool. And then we go down all the way, it's nothing. And then this way we basically classify our image into like all of these different bounding boxes. Into these, classify each grid cell in our grid cell. And then basically in the next step, we define a bunch of anchor boxes. So these are arbitrary that we can define by ourselves. So depending on their shape. And then some of the shapes in the image, so some of the bounding boxes that we can define on our image could fall within this shape of these anchor boxes we've defined. And then when we combine them together, we can then figure out basically the bounding box of our images itself using these anchor boxes. So if you have like a shape that is like rectangular, for example, a person could be a rectangular size like this. A rectangular size anchor box like this allows us to make sure that when we're trying to detect the object, we're in particular looking for that object that fits that specific anchor box. So the main purpose of anchor boxes is just for us to help us demarcate between multiple objects within the same grid cell. So using grid cells as a way to classify, to identify where the objects are is basically one way we can then we use in order to get rid of the second stage of the process, which is basically proposing regions. So Appos asked grid size could have the same issue like the size of sliding box, right? So exactly. So when you define your YOLO models and when you define your single shot detectors, you still need to define your anchor boxes and you still need to define the size of your grid cell. And that the size of the grid cell becomes the input size of your neural network. So when you pass the image in, you also need to pass the size of your neural network as part of your hyperparameters. So this becomes the hyperparameter you have to play around with in order to detect it. This is a typical architecture of a single shot detector. So if you see here, most of the architecture is the same as the other architecture we've seen with CNNs. So you still have the backbone. The backbone always remains the same, even with RCNNs. You have a backbone CNN, and then at the top, at the head of the backbone, you may attach a bunch of SSD layers that perform that classification for you of the grid cells. And then you can then use basically the original prediction layers to perform the prediction of the basically the coordinates of the object itself. I've provided a link here if you want to read more about single shot detectors. But what I'm going to do mostly now is I'm going to focus on YOLO itself, because I think YOLO is more popular in terms of like its usage. And it's actually a model that you can use in production in terms of like its architecture and its methodology. So the YOLO model itself is not actually quite different from the other models in terms of this architecture. You can see it has a bunch of convolutional layers and a bunch of max pooling layers. And it's just very deep. So here you see it has about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's about like 30 to 40 layers deep, right? So it's the full YOLO is a very deep model The tiny YOLO is about 14 layers, so it's not that deep. So you can use tiny YOLO on like mobile applications and run inference on it on mobile. But basically the model itself is just a bunch of like convolutional layers connected to each other. You may also have a bunch of skip connections in between. So what the skip connections allow us to do is it allows you to pass the signal from the earlier layers to the final layers, so that like when you do a backprop, you don't have the problem of vanishing gradients. So that's the main like point with adding some form of skip layers in between. And you can see here actually in terms of average precision, which is the area under the recall precision curve, YOLO is actually doing quite well compared to an RCNN in terms of its recall and precision. So if you remember, recall is basically how well we can identify all the objects in the image, and precision is about how good we are identifying those images that we are identifying. So how precise we are with our detections. So when you plot them together in terms of their performance, you can see and you get this precision recall curve, and then the area under that is the mean average precision. Another way you can think of average precision is like how well the detection boxes fall over on the label boxes, and how well that happens across all the classes, across all the images. So when you take all of those numbers and you average them together, you get the mean average precision. And with YOLO, you get a mean average precision of about like 60% on the mock data set, which is actually quite good. Especially because this is all across like thousands of classes, not just one class. If you try to train a YOLO model on like one class, so if you take a pre-trained YOLO model and then you fine tune it towards one class only, and you get you can actually achieve state-of-the-art accuracy numbers around like 90 to 94% or whatever. So I already showed you this. So YOLO actually can be used in real-time applications. I've actually trained a YOLO model for people counting application in buses using real-time cameras. So on 30 frames per second cameras, and it actually did achieve really good accuracy numbers in terms of like 90+%. And the way actually YOLO works is very similar to single shot detectors. What YOLO does is that it takes an image and it only passes it through a one CNN convolutional neural network. That's why it's very fast, because it only does one forward pass. It doesn't need to pass it through a bunch of other networks like region proposal networks and whatever. What it does is that it takes a grid of SNS grid of boxes in an image. It basically converts an image into an S grid image, and then it tries to perform classification on each grid. So each grid has a responsibility on classifying which most probable class that it belongs to, right? So without anchor boxes, you can only classify each grid cell into one class. It's only when you have anchor boxes that you can then classify each grid cell into multiple classes. So without anchor boxes, you only have one class. So here, for example, we create a class probability map using the SNS grid cell. So once we divide our image into a grid of SNS, S by S, each grid cell then gets classified into one object's classification. And then from that, you also get a bunch of bounding box proposals at the same time. And then when you combine them together, you use a process called non-maximum suppression to kill or get rid of all the bounding boxes that are noise bounding boxes. And you end up, when you combine the bounding boxes and the class probability map, you can then predict to good accuracy where the objects are on the image, as you can see here. And when I say non-maximum suppression, what I mean by that is when you have multiple bounding boxes detected on your image, most of these boxes have so pretty much every bounding box has a probability score as well attached to it, as well as a class. So what you do is for each class, you take the bounding boxes and then you try to see the overlap of those bounding boxes with each other. The ones that have the most overlap you keep them, the rest you get rid of. And then you then try to basically keep the one with the highest overlap that also has the highest probability score in terms of its prediction. So the way you do the overlap scoring is that you take the label and you take the ground truth, which is the blue one, and you take the label and you take the prediction and you calculate the IOU, which stands for intersection of union. And the way you calculate that is that you take the area of the overlap, which is the blue box, the dark blue box, and then you basically divide it by the area of union, which is the combination of areas of the ground truth and the prediction bounding boxes. And you can then calculate the intersection of union. So the intersection of union is 100% if the bounding box prediction and the label prediction bounding box are exactly the same size. It's going to be less than 1, so it's going to be less than 100% if the bounding box of the prediction either is bigger or smaller than the ground truth bounding box, or they're basically just overlap, or they're not there. It's going to be 0 if they don't even touch. So it's the IOU will be 0 if both bounding boxes don't even touch or don't even overlap. So you can actually calculate the IOU like this, and then you use the IOU in conjunction with the overlapping bounding boxes to basically suppress all those bounding boxes that are non-maximum or non-dominant. So you suppress all the non-dominant bounding boxes, and you keep that bounding box, you keep the dominant bounding boxes for each class, and you get rid of all the other bounding boxes that have a lower prediction score. So it's a two-stage process. The first stage, you calculate the IOU of the bounding boxes for each class. You keep the ones with the highest IOU, and then you get rid of the ones in the next stage where their prediction score of that bounding box is low. So you only keep the bounding boxes that have a high IOU and a high prediction score at the end. So that's how you perform a non-maximum suppression. And that's how you get from the image from the left-hand side, all of those bounding boxes, to the bounding box to the right-hand side. So Abbas asks, is there any other algorithm that outperformed YOLO? That's a good question. Not that I've heard of. There are different versions. There are 3 official versions of YOLO at the moment, plus 4 other non-official versions of YOLO that have just like made some small improvements to YOLO itself, like YOLO v4, YOLO v5, and so on. So if there are any algorithms that outperform YOLO, it's mostly using the same methodologies. I'm not sure about the comparison of single shot detectors versus YOLO, but that's another area that you could look into. So basically, what YOLO does is that it takes that image, resizes it down, runs it through the convolutional neural network, and then basically performs a non-maximum suppression at the end. The only difference between YOLO and the other bounding box detectors is that YOLO gives you the bounding box detector using the center and the width and height. So the numbers that YOLO network gives you at the end is the center of the bounding box and the width and height of the bounding box in relation to the grid cells. So that's why it's way more complicated to try to draw these output predictions from a YOLO model, just because it uses the coordinates it gives you are in relation to the grid cell that the center point of that bounding box is basically presented in. So if the bounding box center point falls into the 4th grid cell, you need to then perform the calculation in relation to the 4th grid cell width and height, basically. So the formula for those calculations are here. So if you want to find the BX/BY, which is the center point of the bounding box, and then the BW and BH, which is the width and height of the bounding box, you have to basically take these calculations into account. And you can see the full architecture of the network as well on the right-hand side. And you can see some layers go all the way to like 10,000, 1,024 like filters at the end. So it's a very, very, very dense and deep network, but it has a very, very, very good performance. And it, with tiny YOLO, you might even get way better performance at the end as well. And once you do that, and once you run the network through a video, which is basically, you can loop over a video, like you can loop over basically a list of numbers. So with OpenCV, you can actually loop over, you can read images of a video in. So a video is basically a connection of images per second. So when you say a video has 30 frames per second, that is every second of a video has 30 images baked within it and compressed into an MP4 container or into an AVI container. That's the format of the file. So in order to perform like real-time detection, all you have to do is loop over your video at each frame and then pass each frame to the detector. And then you can then perform a detection for each. And then you basically then write everything back, draw those detections back onto the frame, and then basically write those frames back into a video. And then you can get these video outputs at the end. And we will go into more of the coding part of this, how we can actually train your own detectors and run them inference over the videos in the future workshops. But this is basically how a YOLO model works, and you can actually use it to like run it on your own images. That's a picture of me with a couple of our community members doing a hackathon, and then we just run the YOLO model on this picture, and you can see it has pretty much classified everything pretty correctly. Classified the cups, the keyboards of the laptops themselves, the dining table, the persons, even though we had so many occlusions happening in this video. So it's actually a very good model. And you can even use skip connections in the architecture of the network itself, as I mentioned, in order to reduce the noise, as well as increase the signal when you do a backprop. So with that said, that concludes the workshop for today. I'm happy we have 5 minutes left as well for the end of the workshop, if anyone has any questions, and then we can answer any of the questions you have as well right now. Do you have any questions about YOLO, single shot detectors, RCNNs, or basically application of these detectors on your own data sets? Are there any data sets that you have that you want to understand how you can apply these models onto? So Abbas is asking, when is the next workshop? So the next workshop will be happening, I think in 2 weeks or 4 weeks time from today. So our plan is to run 2 workshops a month. So that's our aim. But if we can't do that, definitely there will be 1 workshop each month. So what is the next step of the research? So at the moment, in terms of the challenges with the YOLO model, is that it's still not very accurate enough. So it achieves about 70% mean average precision across all of the classes. So I guess with new detectors coming out, it's more about not just being able to detect the bounding boxes, but also detecting exactly like the full shapes of the images. The other part of the research would be around the labeling of the data sets. Right now, the models is not just a caveat, it's also the data itself. So it's very hard to label data sets right now. You have to basically sit down and watch lots of videos and like label a lot of videos. And the tools that are coming out there right now is like, for example, there's a tool called YOLO V7, I think, which allows you to then perform labeling of data sets in an interpolated format. So you label 2 images, like let's say 10 seconds from each other, and then the labeling software tries to like label all the images in between for you. So you can save quite a lot of time labeling your data sets and training your own detection models. The other thing I would suggest as well is that at the moment, application of YOLO and like other detectors are quite complicated in TensorFlow. So normally you have to like end up finding a GitHub repo of someone who implemented this YOLO architecture in like TensorFlow version 1, which used to use computation graphs, compared to TensorFlow version 2, which has abstracted away the computation graphs. And it makes it really hard for basically most companies and most individuals to implement their own object detectors. In particular, YOLO was written in its own deep learning framework called Darknet, which is like a combination of C++ and like, I don't know, like some other languages. And it's very performant in that framework, but being able to like constructing this whole YOLO network architecture and logic, because especially it uses anchor boxes and S by S grid cells, and performing like a single pass over the neural network. So implementing those yourself could be quite difficult. So you need to like find other people's GitHub repos that implemented that in TensorFlow, and then like trying to figure out how to convert it back into TensorFlow 2.0. So those are the main challenges of research with these single object detectors, basically. Other questions? Is that perhaps why there is more focus on SSD to bypass this issue? That could be the case, actually, Melanie. So the issue could be with the fact that like, yeah, like even like when you Google right now, TensorFlow tutorials, object detectors, there is just one thing that comes up, which is just TensorFlow object detection API, which sounds like to be just like a abstracted away feature of TensorFlow, so you can just perform some really simple object detection tasks. If you want to like train your own custom object detectors, it becomes a more complicated area, especially when you want to deploy these object detectors onto like edge devices like NVIDIA Jetson Nanos and NVIDIA like devices. Like you will need to just produce the model itself, but we will also need to convert it to a format that is like runs on like edge devices themselves. And the whole process can be really complicated, especially when it comes to retraining it and things like that. So if there are simpler architectures, simpler processes that can be applied, that could be way better. Because as we go forward, we might, if we see that like the process is getting more complicated and more complicated and more complicated, I think this is that is the time that you need to look into outside the box. Any other questions? So Isaac asks, are there any commercial apps currently using any of the current architectures? Yes, so I produced one app myself that uses the YOLO v3 architecture. So not even v4, the v3. So v3 is even operational. And that one actually uses, that runs on empty videos at 150 FPS, and it runs on videos that has people in it at about 30 FPS, not on a computer, actually on an edge device that runs on a GPU. So in real time at a 30 FPS or up to 60 FPS, it doesn't just run the detections on it. It also, on every frame of that video, it also runs a tracker as well. So the detections goes into a tracker, and then it starts allowing us to track people across the video. So that is actually currently deployed on a bunch of nodes at the moment, and it's running in real time. So you can actually start using YOLO v3 or mask RCNNs in real world applications. The main culprit is being able to apply to your own data sets and perform transfer learning on that. In terms of accuracy, you can, it depends on your data set and how much training you do. But if you don't have other dependencies on your application and you only care about like detection, you can achieve really high good accuracies of something between 80 to 95%. Whilst remaining real time. Obviously, it comes down into like how complex your data set is, like what are the edge cases. the positioning of your camera, the lighting conditions, basically all of those things, and whether you have collected enough samples of each type of different condition class, basically. So it's not just enough to collect, I don't know, 1,000 images of dogs. You may also need to collect way more images of like dogs in like, what's it called? Like in bad lighting conditions, in good lighting conditions, in raining weather or whatever, like when they're occluded, half occluded, full occluded, and so on. Any other questions? Thank you so much, everyone. If you have any feedback, Leah, let me know, just drop it in the chat. Just to let you know, we will be running more workshops in the next 2 weeks or in 1 month's time. It will probably be more focused on semantic segmentation and style transfer, but we will also try to basically make the next workshops more hands-on with coding. Hope you enjoyed the session, and I will send you this recording once I've uploaded it to YouTube. Keep a lookout on your email or inbox. See you guys later.